Yeah, thanks, Elden. And thanks to all the organizers for inviting me. I will start by sharing my screen. All right, so this should work, I think. All right, yeah, so this is joint work with Elden, Ryomei, and Ryomei Iwasa and Shane Kelly. And so the theorem I want to talk about today is this theorem right here. This is Milnor excision for motivic spectra, and so it says the following. So if you consider the pre-sheaf of infinity categories given by motivic spectra, so this is pre-sheaf SH here, and it satisfies Milnor excision. And what we mean by this is that if you have a Cartesian square of commutative rings of this form, so it's just a Cartesian square where one of these maps here is surjective. And Cartesianness condition can be rephrased by saying that the morphism A to B maps the ideal I isomorphically onto an ideal of B. So in that situation, if you take SH, if you apply SH to this square, you get a Cartesian square of infinity categories. Immediate corollary of this theorem, which is perhaps more interesting, is that if you take a specific motivic spectrum in SH of S, then the cohomology theory it represents right, so if you have a motivic spectrum, then there's an associated cohomology theory which is defined on the category of S schemes, valued in spectra, for example, then this will satisfy Milnor excision as well in the right. So let me mention there's a non-commutative analog of this result due to Land and Tamer, which says that if you have a localizing invariant of stable infinity categories, which is truncating, and truncating means that it basically means it's derived invariant. So if you have an E1 ring, the value of the invariant depends only on pi 0 of the ring. Then any such localizing invariant satisfies Milnor excision. So this can be regarded as an analog of this theorem about of the previous corollary, because while localizing invariants are also known as non-commutative motives, and so this is somehow a non-commutative analog of SH in some sense. Usually one does not consider A1 invariants in this context, is because somehow these localizing invariants satisfy this projective bundle formula, which replaces A1 invariants for many things. So, well, anyway, the truncating assumption is something which, well, if you define SH for connective E-infinity rings, which you can, then the cohomology theory represented by motivic spectra would be truncating in that sense. So it's kind of closely related result. Right, so let me just go over some examples of this phenomenon of Milnor excision, more or less classical examples. So first example is this due to Ferrand, that if you take the functor which is represented by a scheme, then this always satisfies Milnor excision. Yeah, I mean, this can be generalized a bit to algebraic spaces and beyond, I believe, but this is a fairly classical result, but this is also not entirely obvious. I mean, this is saying that if you take the spec of the square, you have a co-Cartesian square in the category of schemes. And then second example is vect. So by this, I mean the category of vector bundles. And so this satisfies Milnor excision, and this is kind of the original result of Milnor, which gives the name to this property. And then the perf, the infinity category of perfect complexes also satisfies mean excision. And so, which is due to Lurie, I believe. And then there's some variants. So K-theory itself is a well-known non-example, so it does not satisfy mean excision, but there's some variants which do. So KH is Weibel's homotopy, invariant algebraic K-theory, which satisfies mean excision as proved by Weibel, and then K-inf, that's the fiber of the cyclotomic trace map, and this satisfies also mean excision. This was proved by Land and Tamme. And both of these, KH and K-inf, this can be regarded as a special case of the Land-Tamme theorem here. So they're both localized, they're both truncating and localizing invariants. Yeah, so in particular for these, you get mean excision for non-commutative rings as well. Yes, I did not mention. But if you only care about commutative rings, then KH is also a special case of the corollary here, because there is a motivic spectrum usually called KGL, whose associated cohomology theory is precisely KH. And last example due to Bat and Matthew is étale cohomology with torsion coefficients. So this always satisfies mean excision. And this is also a special case of this corollary, provided that the torsion in this sheaf F is co-prime to the characteristics of S. In this case, there will also exist some motivic spectrum which represents this cohomology. But you don't need this assumption for the results. Okay. So, yeah, so the goal for today is to actually go through a proof of this theorem. Yeah. So, and there's so this proof uses a criterion for mean excision, which in this talk I'll just use this as a black box. But so it's yeah. So if you have some functor f and commutative rings valued in some compactly generated infinity category, and assume that it's a finitary CDH sheaf, and so finitary just means that it preserves filtered colimits. And CDH sheaf, well, it's a sheaf for the CDH topology, and I don't want to really give you the details on what the CDH topology is, but I mean, okay, a very easy, quick way to define it is to say that the points of this topology are precisely the Henselian valuation rings. And I mean, it's a, so the sieves for the CDH topology are sieves are generated by morphisms locally of finite presentation, and the points are the Henselian valuation ring. So this completely determines what this topology is. It's a cheap way to define it, and then for such a CDH sheaf, the following equivalent, so it satisfies mean excision, or condition 2 here, which is a special case of mean excision. So for every Henselian valuation ring of finite rank V, and every prime ideal in V, this square is Cartesian. So you have V, you have the localization at the prime, the quotient, and the residue field here. So I mean, I'll come back to this notion of valuation ring of finite rank later if you don't remember these definitions. But here, let me just point out that the assumption that V is a valuation ring implies that this square here is actually a Milnor square. Yeah? So 2 is a is just a special case of 1. Right. So yeah, I mean, I've given talks on these topics previously, and I usually talk about the proof of this criterion, which is also quite interesting, I think. But for today, I want to take this as a black box and tell you how to say something about SH using this criterion. Okay, so any questions so far? Okay, so let me give the definition of SH for you. So I'll define it, well, since Milnor excision only involved rings, I thought maybe a good idea to define it using only rings. But so if you have, right, so first I define motivic S1 spectrum, and this is simply a functor on smooth R algebra, so this subscript here means smooth, to spectra, which satisfies these two conditions, a one invariance condition, and the so-called Nisnevich excision or Nisnevich descent condition, which can be phrased this way. So if you have an étale morphism of rings, which is an isomorphism modulo F for some element F in A, then this square should be Cartesian. For any such functor, you can define the contraction x minus 1. And so this is defined to be the fiber of the evaluation at one map on Laurent polynomials. And because this evaluation by one map has a section, this is in fact a direct sum and decomposition like this. And so this defines x minus 1. And I mean, this is also, I mean, if you think about it geometrically, this just means take the GM loop space of x. That's what x minus 1 is. Right, and finally, a motivic spectrum over R is simply a sequence of functors x, which are contractions of one another. Right, so of course, any term in this sequence determines all the previous terms, so the sequence only matters, you know, as you go, as n goes to infinity. Okay, so here's some basic facts about, so motivic spectra, this is the infinity category of motivic spectra is what SH of R is. So this category is compactly generated. This is actually fairly clear from the definition that I gave that this is the case. It's basically because all these conditions are kind of finitary conditions, yeah, only involve finite diagrams and so on. So if you look at SH omega, so this means omega means the compact object in SH. This is a finitary CDH sheaf. Right, so I mean, it will be a CDH sheaf without the omega as well, but I take the omega so that it becomes finitary. So if you take SH itself, the large category, then it will not be finitary. Or, I mean, it will be finitary if you regard it as taking values in co-complete infinity categories. But co-complete infinity categories don't themselves form a compactly generated category. So, I mean, the idea is that we'll want to apply this criterion here, which has this assumption that C is a compactly generated infinity category, which is kind of an important assumption. So we have to. So this is why we want to look at pass it to compact objects here. Right, and the last observation is that if you have a Milnor square, then SH of this square is going to be Cartesian if and only if it is so on compact objects. And there's one implication in this statement, which is kind of formal. If you take compact objects, this will preserve Cartesian squares. I mean, for any square of compactly generated categories, basically. The other implication, however, is a bit more subtle because so if you have a square of small categories and you take int, pass to int objects, then this is not, I mean, this operation does not necessarily preserve, does not preserve Cartesian squares in general. But it does if one of the functors along which you're pulling back has fully faithful right adjoints. And so this is the case here. This functor from SH of A to SH A mod I, so this is like a pullback along a closed immersion. And this has a fully faithful right adjoint. Right, and this is, this is a non-trivial fact, which is not at all obvious from the definition. So it's a consequence of the localization theorem of Morel and Voivodsky, and one of the basic features of this infinity category SH. Okay. Right, so the point is we can apply now this criterion to the pre-sheaf SH omega, taking value in the infinity category of infinity, of small infinity categories, which is compactly generated infinity category. And taking into account this last observation here, the main theorem is reduced to the following special case. So if you have V a valuation ring of finite rank and P a prime ideal, then this square of infinity categories should be Cartesian. Right, so it would even suffice to prove this just for a Henselian valuation ring according to the criterion, but this will not help in the proof. And of finite rank, so we will use in the proof that V is the finite rank, but of course the result is true without that assumption, since in any case it's a special case of Milnor excision at the end. Yeah. But according to the criterion, it suffices to consider a valuation ring of finite rank. All right, so here's some notation for this situation. So X will be the spectrum of V. U is going to be the spectrum of the localization, which is an open in X. And Z is the quotient, which is closed. And T will be the open complement of Z. Okay, so this is the picture here. So evaluation rings are one way to define evaluation ring is it's a ring where the ideals are totally ordered under inclusion. So in particular, the prime ideals will form a sequence like this of specialization. So here it specializes from right to left. So the rightmost point is the generic point and the leftmost point is the closed point, which is the maximal ideal. And the rank, in this context, the rank just means the Kroll dimension of this valuation ring. Yeah, so finite rank just means there's only finitely many points. And yeah, and so you have some random prime in the middle here, and then the quotient V mod P is this Z here, this closed subscheme, and the localization at P is this open subscheme. So in particular, I mean, yeah, the fact that V is finite rank also implies that localizations at prime ideal is always an open subscheme. Right, and this T is just the open complement of Z, so T is contained inside of U. Yeah, it's just U minus its close point, which is P. Okay. So, and here I just give names to these various maps. Yeah. So U is the open immersion of U into X and I of Z into X. And these squares are both Cartesian squares here. Okay, so we are trying to prove that some square of infinity category is Cartesian. So let's just think for a second how to approach such a question. And I mean, there's basically well, there's one way to approach this, which is just to look at the gap map in the square. I mean, you want to show that the square is Cartesian, so you look at the comparison map here from the corner to the pullback. And then this functor will have a right adjoint for formal reasons, which is given by this kind of gluing formula. Yeah, so if you have some object over U and object over Z, which are identified over the intersection, then you can kind of glue them together like this. And this is the right adjoint to the restriction functor. So we're trying to show that this adjunction is in fact an equivalence of categories. I mean, if you remember how one proves Milnor excision for vector bundles, for example, versus the original instance of this, the beginning of the proof is exactly like this, basically. I mean, it's exactly the same strategy of proof. Right, and now another feature of this category SH is you have this Recalmont situation whenever you have an open-closed, a complementary open-closed pair in a scheme X. Yeah, so Z is a closed subscheme of X, and T is the open complement. So you have this Recalmont. You have these 6 functors here, and in particular, this implies that pullback to Z and to T is a conservative pair of functors, and because T is contained in U here, this implies in particular that these 2 pullback functors to U and to Z form a conservative pair. Okay, and I mean, this is useful because to show that this adjunction is an equivalence, since one of the functor is conservative, then it remains to prove that the other functor is fully faithful. Let's see. Right, and so if you unpack what it means for this right adjoint to be fully faithful, so this again, everything is very formal here. So you have these, so these two maps here are the two components of the co-unit maps of this adjunction. And so a full faithfulness is just saying that these two canonical projections should be equivalences. And then if you think about what is going on the left-hand side here, particularly using the fact that all the morphisms involved here are immersion, so all the push forwards that appear are fully faithful functors in this formula. And so it really boils down to understanding how, in this case here, how the pullback along U commutes with the push forward along I. And you have this smooth base change formula because U is what's an open immersion in particular. It's a smooth morphism, so the smooth base change formula tells you that this canonical natural transformation is an equivalence. So let me just show you again the squares. Yeah, so K and V are the morphisms in this Cartesian square here. So base change formula says that pushing forward here and pulling back here is the same as pulling back here and pushing forward here. And this is exactly what you need to justify that this morphism is an equivalence. I mean, in fact, this is even if and only if you think about it, but anyway, we only need this implication from right to left. And now if you look at the second morphism here, again, to see that this is an equivalence, we need this kind of other base change property where we now push forward along the open immersion and pull back along the closed immersion. Right, and again, this is an if and only if implication, so we have to prove this base change property. But this base change property is not, I mean, it does not hold for any known general reasons. This is neither an instance of smooth base change nor a proper base change. So yeah, so this is a weird base change property which happens to be true in this very specific situation of evaluation. Okay, so let's see. Yeah, so there is another reduction that one can do. One can rephrase. So this is just a reminder of the notation here. So one can rephrase this base change property in terms of these extension by zero functors for these, which only involves the open immersions. So with this, I don't want to, I think, go over the details of this deduction. I mean, it's just basically playing around with the two recalments for these complementary open closed pair here. I mean, in fact, yeah, this diagram on the right explains this equivalence. Yeah, the two rows here are co-fiber sequences. And yeah, the vertical maps are these two natural transformations here. So they're simultaneously equivalences. But I mean, it's just a convenient way to rephrase the question in a way that only involves these two open immersions. So yes, let me actually restate the previous theorem now. So this theorem is equivalent to the previous one. So if you have a valuation ring of finite rank and you have two open immersions inside of there, with a crucial assumption that T is not equal to U, yeah, so T is a strictly smaller open than U, then this canonical natural transformation is an equivalence. Right, so as I said, these Schwick functors are the extension by zero functors. So you always have this canonical natural transformation from the extension by zero to the push forward. And this transformation is basically never an equivalence by itself. Yeah, I mean, unless your open immersion is also a closed immersion, otherwise it's not an equivalence. So in particular, this is definitely false if T is equal U, for example, because then that would just be saying that extension by zero is the same as the push forward, which is not true. Well, what this is saying is that the extension by 0 and the push forward, they agree if you plug in a sheaf, which is itself extended by 0 from this strictly smaller open subset. So I think intuitively, this is something that makes sense. Yeah, and in particular, if you consider, if you just think of this, just pre-sheaves on this topological space X here, then you will see that this is in fact true. Yeah? So this is not an unsurprising statement, just looking at the topology of this spectra evaluation ring. Okay. Any questions up to this point? Right.
Sorry, Mark, can you say once again, if you don't mind, the topological explanation why they should be the same? I didn't follow.
Right. I mean, if you consider this this natural transformation just on sheaves on this on a topological space of this form. Right. So I mean, what is the topology on this space? The opens are all the intervals on the right. So these are all the opens like this. So this is like a Sierpinski type topological space. Yeah. So I mean, I'm just saying, if you write down, I mean, if you just take a sheaf on one of these open, I mean, you can just write down what both of these functors do completely explicitly. One is extension by 0 and one is push forward. So you just write down the formulas and you will see that they are the same.
Okay, thanks.
So I mean, I think to really convince yourself, I think you just have to write it down. I mean, I will do it. I will do something. Well, I basically do that later in a slightly more complicated context. But yeah, I mean, I'm just saying this is not a completely insane to think that this might be true a priori. Right. But now with this, so the point of this reduction, so now we can forget about this Z in particular. We just have to remember we have spectrum of this valuation ring and we have two opens inside, one strictly smaller than the other. So it's a very simple geometric situation. Right, and so here's the idea of proof. And the idea of the proof is, so we have a statement about motivic spectra, and the motivic spectra like, well, they're like GM spectra in some kind of sheaves and so on. So we'd like to reduce the statement to the analogous statement at the level of pre-sheaves on smooth schemes. And I mean, this is a good idea because if you actually, consider this statement, you will see that it is true. If you just consider the analogous statement for pre-sheaves on smooth schemes, then you can actually check it directly by hand. It's not very difficult. Okay, so I mean, this gives you hope that you can deduce this statement about SH from this, but this does not work, unfortunately, because of the following problem, that the push-forward functor U lower star is not compatible with the Nisnevich topology, so in the sense that it does not preserve Nisnevich local equivalences. So even though we do have this formula at the level of pre-sheaves, we do not have it at the level of Nisnevich sheaves. Because of this problem with the push forward along an open immersion. So in Nisnevich topology, so if you're pushing forward along a closed immersion or more generally along a finite morphisms, then this would be compatible with the Nisnevich topology or the étale topology. So this, but if you push forward along an open immersion, then definitely not. And the solution to this is to somehow replace the Nisnevich topology by the CDH topology. So we'll see that for the CDH topology, push forwards along open immersions are well behaved. I mean, they preserve CDH local equivalences. But okay, so yeah, so how are we going to make use of this idea? So we have to define a CDH version of the category SH. So SH CDH ring R, and it's exactly the same definition, except that instead of Nisnevich sheaves here on smooth schemes, we now take CDH sheaves on finitely presented. So FP here means finitely presented R algebras. Right, so and the CDH sheaf is a topology which is finer than a Nisnevich topology. So if you have such a pre-sheaf, such a CDH sheaf, you can restrict it to the subcategory of smooth algebras, and it will be a Nisnevich sheaf there. So you have a forgetful functor from right to left here, from SH CDH back to SH, just by restricting all of these XNs to smooth schemes. And this forgetful functor has left adjoint, and then there is theorem of Szysinski that this left adjoint functor is fully faithful. Yeah, so right, so this theorem, so this is an easy consequence of the fact that SH has CDH descent, which I already mentioned. I mean, which we're already using as a background to this proof. So it implies in particular this fact that the functor from SH to SH is fully faithful, and the nice consequence of this is that any type of push forward functors that you have on SH can be computed via SH CDH in the following sense. Yeah. So these functors here, you can first go to SH CDH, then apply the analogous functor, and then restrict, and these squares will commute. So a priori, if you did not know that this functor was fully faithful, what would be kind of obvious is that the lower shriek functor commute to the left adjoints here, and the lower star functors commute with the right adjoints. But because this functor is fully faithful, then in both cases you have a commutative square like this. Yeah, so because of this, we can consider a stronger statement now, that in the previous situation, so you have this X, which is again the spectrum evaluation ring of finite rank, and this opens U and T, then the extension by zero and the push forward agree in that sense. Yeah, now on the category SH-CDH. So this is, well, this is at least, well, this is a stronger statement than the previous one, so it implies what we want to prove. Okay, so here's the fact about the CDH topology that I alluded to about pushing for an open immersion. In fact, I state here a slightly more general statement about etalmorphisms, but in particular, so I mean, we apply this, we're going to apply this to this open immersion here. So if you have an etalmorphisms between quasi-compact, quasi-separated schemes, then the push forward functor on pre-sheaves, P sigma, so P sigma are those pre-sheaves that send disjoint union to finite products. And this push forward functor preserves CDH local equivalences. Or equivalently, it commutes with CDH sheafification. Right, so the proof of this is very easy. Basically, you want to plug in here in this formula Y Henselian valuation rings. So the Henselian valuation rings are the points of the CDH topology. And now this fiber product Y times U is some quasi-compact, quasi-separated scheme with an étale map to the spectrum of Henselian valuation ring. And it turns out that such a thing is necessarily a finite disjoint union of spectra of Henselian valuation rings. So just a little structural results about these Henselian valuation rings. I mean, it's similar to if you have something which is finite over a Henselian local ring, then it's itself a disjoint union of Henselian local rings. But yeah, the point is if you now look at valuation rings, then the same statement is true with finite replaced by étale. Yeah. Right, and I mean, this proves the result. I mean, basically, if you have some CDH local equivalence from F to G here, because these functors, so this is why you have this P sigma in the statement, yeah, because these functors are in P sigma, they transform this finite disjoint union into a finite product of Henselian valuation rings. And so if you have some natural transformation from F to G, which is an equivalence on Henselian valuation rings, then this will still be the case if you plug in a fiber product like this. So this is precisely saying that the push forward preserves local equivalences. And while you might object that in this generality, you may not be able to detect equivalences on stocks, and this is true, but nevertheless, this argument proves the result because the CDH local equivalences are generated by monomorphisms. Yeah. So in fact, to prove this, it suffices to check preservation of CDH local equivalences are also monomorphisms. And for monomorphisms, you can check if it's an equivalence on stocks in any case. So when the push forward functor U lower star preserves monomorphisms. So yeah, so this is good enough. Yeah, so this is very basic result somehow, but we were nevertheless a bit surprised by this because, well, as far as we can tell, there's this basic observation has never been used before somehow about the CDH topology. But okay, now it plays a crucial role in this proof somehow. Okay, any questions on this? So using this lemma now, it's easy to reduce this statement here to the pre-sheaf level. So, so basically the CDH localization, I mean, the topological localization is really the only potential obstruction to this reduction. I mean, you also have to consider that SH consists of like this GM spectra, and you also have the A1 invariance condition. But neither of these pose any obstruction to this reduction. So it's only the topological obstruction, and this lemma resolves it. So we can just reduce another question to comparing these two push forwards at the level of categories of P sigma pre-sheaves of spectra on schemes of finite presentation. Right, and I mean, this is now really the heart of the proof, and we just check this by hand, so direct computation. Just remember the definition of these push-forward functors. Okay, there's one tiny observation here, which is that because X, so X is always in this statement the spectrum of a valuation ring of finite rank. So in particular, it has finitely many points. And so any scheme of finite presentation over X will be the sum of its connected components, finite sum of its connected components as a consequence. And because we're looking at pre-sheaves in P sigma, it suffices to compute these functors on a connected scheme. Okay, so it's a minor observation. So let's assume that Y is a connected scheme. And we just write down what these two push forwards are doing. So the first one here is just extension by 0. So, well, it just extends by 0. So the value is just the value of f if Y was over the open T and 0 otherwise. And for the other one is almost the same formula, but now you have the push forward instead. So you get this. Yeah, so YU, this is the restriction of Y to U. So these are the formulas. So then the claim that we're trying to prove is that these two formulas are equivalent. Yeah. So, and so here's again a picture of the situation. So I have this valuation ring and these two opens, T and U, and crucially, T is strictly smaller than U. Yeah? So there's a non-empty piece here. And so the key fact that makes this work is the following, that if you have a connected scheme mapping to the spectrum of a evaluation ring, the image of the map is always an interval in the specialization poset. I mean, there's an interval in this picture in the obvious sense. Right, so if we, let's just take this fact for granted for a second, then it's very easy to analyze, what is going on. So you have some Y mapping here, and the image is some interval in this picture. So you can just basically, go over all the possible cases of where this interval might lie in the picture, and then compare these two formulas in each case. And you will see that they agree every single time. I mean, basically, the only way that they would disagree is if the image of Y had some part which was in T here and some part which was outside of U like this. I mean, if this was possible, then these two formula could differ. But the point is, because it's an interval, then it actually has to be like this, and then it's fine. So right. So I mean, I'm not gonna go over all the cases. Yeah, this you can check that for yourself. But this right. So I guess that's the last thing I'm going to say is to explain this key fact. So really, everything boils down to this. To this fact, and I mean, this is a very elementary fact as well, but this is really a fact about commutative algebra, because I mean, if you think about just the topology of the situation puts absolutely no constraints as to what the image of Y might be, because so you have to remember that the topology on this picture here is not the it's not the interval topology. It's like a Sierpinski type topology. So every subspace of this topological space is connected. Yeah. So just knowing that Y is connected implies nothing about the image of a continuous map to this topological space. So it's really a result about commutative algebra. So let's say, to prove the key fact, we can assume Y is an affine scheme. We can also assume that A is reduced. Yeah, that we only care about the image of the maps. That makes no difference. So what we're gonna do is take some prime ideal in the spectrum of V and assume that it is not in the image of Y. Yeah. And then the goal will be to show that in such a situation, Y necessarily split as a disjoint union of two pieces. Yeah, one which maps to the left of P and one which maps to the right of P. So this is equivalent to the statement that if Y is connected, then the image has to be an interval. Okay, so we have the following diagram here. So I want to look at this morphism in particular. So A is just an algebra over the evaluation ring V, and we have an exact sequence here. So the exactness of this sequence is just because these four rings form a Milnor square. Yeah? I mean, this is also injective, so this is really an exact sequence like this. And this square is a push-out square of commutative rings. And so the co-kernel of this morphism here is precisely this ring here. Yeah? So the assumption that this ring is zero means that this morphism is surjective. And now I claim it's also injective, and this is why we use the fact that A is reduced. A being reduced means that it injects into the product of its residue fields, like so. And this morphism here is completely decomposed morphisms. Yeah, I mean, this is just a cover of spec V by a closed and open. So so any morphism from V to a field factors through this cover. And because it's a push-out square, it factors in particular like this. And so this morphism to these fields factors like this. And of course, now this implies that this morphism is also injective. And so it's an isomorphism. Yeah. All right, so what we've shown is assuming that some point on spec V is not in the image of spec A, then spec A now has to be the disjoint union of two pieces, yeah, one to the left and one to the right of B. And so it's just a rephrasing of this key fact here. So this is what we wanted to prove, and I mean this completes the proof of the theorem. So, and that's all I wanted to say. So, so I stop here.
Sorry, can you show below the page?
Yes.
Yeah. So yeah. Thank you.
Yeah. Let's thank Marc for the talk. Any questions for the speaker?
Marc, I had a question.
Yes.
Can you hear me? Okay.
I can hear you. I don't know who you are.
Oh, this is Gabriel Angelino. So in your like second main theorem, the proof you gave, or yeah, I was hoping it'd be clear to me from the proof, but it wasn't. So in the second main theorem, it seemed like you proved something about not the compact objects, but just like the whole bigger category.
Yes.
But then in your application, you use the compact objects version of it. And
yes.
so it seems to me like you're using the formal version of the results you said earlier. So I was kind of wondering if actually what you prove here is the statement about the compact objects, and then you actually use the non-formal version to get this statement. And then,
so, I mean, both versions are true. I mean, with or without the compact objects. So yeah, so I mean, I was implicitly using this last observation here, that for Milnor square, these two SH or SH compact makes no difference. And
right. So I guess what I was wondering is, do you really prove the statement for the compact objects for the second theorem?
Well, we prove it directly for the large category, but it implies it for the compact objects as well.
Okay. But so then it doesn't seem like you need this hard direction then, right? Because you only use the formal direction for this theorem.
No, you need it. You need it after applying the criterion to deduce Milnor excision at the end, because really what we need to prove, because we need to pass the compact object to put ourselves in the setting of this criterion. So the conclusion is then that SH omega satisfies Milnor excision, and to get the result for SH itself at the end, we need the non-trivial implication.
I see. Okay, thank you.
Yeah.
Any other questions?
I had a question, and you've looked into the future and seen what I'm going to ask about by highlighting this box square. Since you prove this without the Henselian condition, I mean, do you get, in some sense, a stronger statement than, I mean, is there a Milnor excision-y way of saying what you get? Because you prove something that I guess is strictly stronger than Milnor excision.
No, you don't get anything stronger than Milnor excision, because, I mean, even if V is not Henselian, this is still a special case of Milnor excision.
Okay.
So it's just that, I mean, the Henselian assumption is not used in the proof, I guess. But
yeah, okay, fine, okay. Thanks.
I mean, this does mean that we could deduce Milnor excision by knowing only that SH is an RH sheaf, yeah, instead of a CDH sheaf. Yeah, so RH is like CDH with the Zariski topology instead of the Nisnevich one. So the same criterion holds for RH sheaves, which is a weaker descent condition. If you know,
I see.
If you know this result for not necessarily Henselian valuation rings.
For finitary RH sheaves, okay.
Yeah.
Are there examples of those guys, but not Nisnevich?
Of RH sheaves? That's a good question. I don't know any examples actually. That's I think, yeah, things are I chiefs and not CD chiefs. I don't know. Yeah, actually, I'd be curious to know if there's natural examples of this. Elden is thinking.
All the transfer stuff implies immediately Nisnevich, right?
Yeah.
So.
I mean, immediately is.
Yeah, okay, right. Yeah. Any Voevodsky type sheaves all have, you know, CDH immediate. Yeah. Well, L-zar equals to L-nis in many cases, as you know.
Yeah.
So yeah, one more question. I was wondering if you have any idea of like a way to prove some generalization of like the land Tama result that's sort of like I guess like relax some conditions here.
I don't think so. I mean, there's already so few conditions that it's hard to imagine that there even is a true statement with weaker conditions. So, I don't know. So I don't think so. I mean, well, you'd have to ask Landon Tamer, I guess, but my intuition is that the truncating hypothesis is absolutely crucial, and if you weaken it, it's not going to work.
Sorry, I guess I meant the theorem that doesn't use truncating, like where you can measure the failure of it being a pullback, or like or after applying K theory, measure the failure of it being a push out. I guess. Okay, that doesn't matter there.
Oh, I see. So you're wondering if in the commutative setting you could have a more refined theorem like this, maybe. Yeah, I mean, I have not thought about this. I mean, something that might apply to non-A1 invariant things, maybe. Yeah, who knows?
I also have a question. So you have this. If I was only interested in KH, then your theorem goes through, proving it for SH, the functor itself, right? Does your theorem somehow reduce in a nice way to give a proof for each individual represented theory, like KH?
It does not, I think. Yeah, so I mean, somehow, yeah, the proof, right. So, I mean, this is an interesting point, yeah, because if you try to prove Milnor excision for a specific spectrum E, or even if you try to prove that every cohomology theory represented by a spectrum satisfies Milnor excision, this is still weaker than the SH statement. In fact, so in terms of this, so in terms of this Cartesian square here, this corresponds to the left adjoint functor in this adjunction here being fully faithful. Yeah, so the full faithfulness of the left adjoint here is a statement that every cohomology theory satisfies excision. And as you see from the proof, we never prove directly that the left adjoint is fully faithful. And in fact, we would not know how to do this directly. So the categorified statement allows us to prove this by seeing that it follows from the right adjoint being fully faithful and the conservativity of the left adjoint. So this is, so somehow we completely bypass having to prove directly that cohomology theories satisfy excision because of this categorified statement.
This is cool.
Yeah.
I mean, there was the first attempt even, like we couldn't prove this left adjoint is fully faithful.
I mean, sometimes I mean, it seems, I seem crazy to think of proving something for SH directly, but it turns out that was a good idea to think about it. Yeah, otherwise we would not have found the theorem.
Any other questions? If not, let's thank Marc again. recording